Thanks, everyone, for coming. My name is Konstantinos Karagiannis, Global Technical Lead for BT's Ethical Hacking Team. But before I got into the world of hacking, well, I shouldn't say before because I did it as a kid too, but I started out as a physics major and never really strayed too far away from it. So this talk kind of gets to marry those two worlds together for me. So we're going to be talking about quantum key distribution and more importantly, the need for something like this, and how quantum computing is going to shake things up a bit. So recently, of course, no surprise here, everyone knows about Heartbleed and how people panicked when they had to change their passwords at 10 sites, 20 sites. It was a big hassle, a lot of paranoia. Now imagine if one day soon you had to change your password everywhere, and even that wouldn't be enough, because every transmission you sent ever over the internet could possibly be decrypted like that. So that's a very real possibility. We're going to be looking at the kind of sea change that quantum computers are going to make and some of the things we have to start thinking about to protect us in the future. So first up, Richard Fineman said, I think I could safely say, no one understands quantum mechanics. If that's true, I guess you can all file that now. I'll follow you out of this room, and we're done early. So maybe we'll just try and look at some of the basics that we need to understand this part of the topic. One of the most interesting things he said was in 1982 that to simulate reality, because it operates on a quantum level, you'd need to have a quantum computer. That would bring us down to the lowest level of reality. And in a sense, the universe is a 13.7 billion-year-old quantum computer, too. So we're getting really close to being at that pure level of true interactive nature with data. So where did quantum mechanics come from? In the 1800s, scientists thought they had it all figured out. They just thought they needed better measurements of things. Once you get those measurements, they knew how the world worked, Newtonian mechanics, we were all good. But then other little things started to appear, and we realized we didn't know everything. One of the biggest was black body radiation, the idea that if you have something like a burning log in a fireplace, its frequency will keep ramping up with intensity such that after you light a log, in a few minutes, you'll be obliterated from existence. Now, that usually doesn't happen. So we knew there was something wrong with our understanding how energy is emitted. So one morning, Planck was having oatmeal, and he noticed that it was clumpy. At least that's how I think it happened. And he got this idea that what if energy is released in bundles or quantized quanta? So that's where the word quanta comes from. It literally means like a bundle of energy. So he proposed this idea, and he came up with the equation E equals HF. And in it, there's Planck's constant. That's 6.626 times 10 to the negative 34th. Write that down. There's a test. He basically found that if you multiply that, the math works. And he was able to show that energy is released in these discrete forms. No one knew why yet. So earlier, people had experimented with the wave nature of light. There's the famous double slit experiment, Thomas Young, 1803. We saw that if you shine light through two slits, you get dark and light bands. The waves positively or negatively interfere with each other, and you get that. Well, Einstein saw in 1905 that because of the photoelectric effect and the way it behaved, maybe light can be a particle too. And in fact, he said it was a particle. He didn't come up with the term photon, though, that came out in the 20s. So here we have a situation where light behaves as a wave and a particle. Well, it turns out that it also applies to particles that aren't light. So everything in this quantum world seems to behave as both a particle and a wave. And that's something that these machines are going to exploit. So the first evidence of that was Taylor in 1909 saw that this interference pattern will form even if you're dealing with one photon at a time. So this is what you'd expect to see if particles were little balls floating through space, right? If you fire them through two slits, you'd expect to see these two lines of particles pooling up at the other end. Now, that's not what we see. When we send particles, we start to see a waveform. Now, there have been numerous theories about this. The particles are interfering with themselves in other universes is a great one. That was put forth by Everett. It was actually his PhD paper, and he was kind of ridiculed for it, the idea that there are many worlds. But now science is starting to accept that over any other interpretation. But whatever's really going on here in this quantum weirdness, we're getting the idea that particles behave as waves. Now, what happens if we send one at a time? We still get the same pattern. They're interfering with themselves. So when that particle goes through, it's an actual wave function, a mathematical probability that it'll go through the left or the right. And that mathematical probability seems to interfere with itself. What's fascinating about quantum mechanics is probability doesn't describe quantum mechanics. Probability is the thing, is quantum mechanics itself. You can see this with the half-life beryllium atoms. If you have them start decaying and shine a laser every 60 nanoseconds or so, the half-life will reset, and they'll never decay. They'll be like, ooh, he saw me, ooh, he saw me, and they'll never decay. A watch pot literally never boils in the quantum world. So what happens if we look at one of these slits? If we say, hey, particle, are you going through left or right? Well, once we look, this happens again. The particles go, oh, he's on to us, and they start to behave like little discrete cannonballs again. Now, that's horribly confusing. How do these things know? Well, obviously, taking an observation collapsed that probability to a definite amount, and the universe just behaves that way. It's a pretty strange place. Now, that concept of observation, making an observation, that leads to something called decoherence. So when you observe either slit, you get a destruction of superposition. The particle can no longer be in both places at the same time. So decoherence is really important to quantum computing, because to get some of the weirdness in quantum mechanics to apply to a computer, we need to be able to control that state of decoherence. We only want it to happen when we're ready to get our answer from the machine, not before that. Now, it's really hard to maintain this because the universe makes observations all the time. There's so many particles in here, in this room right now, we couldn't even count them. So if a quantum particle appeared right in the middle and floated for a split second, it would be observed by the room and it would just vanish. It would become a classical particle again. So Einstein didn't really like this. He particularly didn't like something called entanglement. Now, entanglement, and we're going to explain it in a second, it basically allows for something he called spooky action at a distance. So some of his favorite quotes are that, and also God does not play dice with the universe. So what really bothered Einstein about this will become evident. Entanglement, if you were to take two particles and create them together in such a way that they're bounded on the quantum realm, they would share a state called entanglement. So it's hard to talk about what really goes on at that level, but we like to use something called spin. So you can simply say that one particle spin up, one is spin down. So if you have an entangled pair of particles, they'll exist in a spin-up, spin-down state simultaneously, a superposition of states. Until we observe, they're going to stay that way. So if we take one particle in a spin-up, spin-down state and the other, and separate them by miles, light years, in theory, you could separate them by a distance of a galaxy. It doesn't matter. What'll happen is, the instant you take an observation of one of the particles, you know instantly what the other particle is. So think about that. If we have these particles separated by the size of the galaxy, and we take an observation of one and see that it's spin up, we'll instantly know the state of the other particle millions of light years away. Well, in that case, hundreds of thousands of light years away. So Einstein hated that because it seems to violate the speed of light. So, is it really an instant violation of the speed of light? Well, not exactly. The speed of light is protected, and relativity protects it, because locality has useful information associated with it. So there are all these thought experiments about, can you use the speed of light to go back in time and warn yourself about something or whatever. You really can't, because the useful information has to be there. So what are we sending if we do this? If we separate these particles and make an observation, we're sending purely random data. Okay, so that's not really useful. We can't force it to send zeros and ones in a spin-up, spin-down state. So there's no way to instantly send information and violate the speed of light. You can use this property for some pretty cool things, though, as we found. So. Oh, sure, why not?
How do you define observation? I mean, how do you define observation at this point when you say before we observe it?
Okay, so it depends on what the particle is and what state you're looking for. Simple would be a photon. Let's say you're using, and we're going to use that example, it's polarization. So once you observe the polarization and figure out that it really is 135 degrees with one particular basis, it no longer is any other state. So it collapses. So you have to have the right equipment. And we don't have time to talk about quantum teleportation today, but it also doesn't violate the speed of light because you have to literally call the person at the other end of the world or whatever and say, hey, set your detector to do this, this, and this, and I'm sending you a particle. Once you do that, you didn't violate the speed of light. You use the phone. So that, of course, travels at the speed of light. So now what can we start doing with this weirdness? First, we enter the qubit here. So unlike bits, which we're all very familiar with, zeros and ones, qubits can be 0 and 1 together in a superposition. They can be represented, you can visualize it as like a sphere where any point moves up and down and gives you varying percentages likelihood that it'll be up or down, for example, 0 or 1. You can display it mathematically. And once we have this kind of spooky particle that could be multiple things at once, we can start to apply it using quantum algorithms to do something very, very different, to do things that a classical computer couldn't do with all the time that we have left. Now, qubits weren't really invented for this purpose. When Wiesner invented them in '69, he was thinking about stopping counterfeiters. So he came up with this great idea of putting 20 photons trapped in a specific state on a bill. And then the bank would be able to analyze the state of those particles and know instantly if the bill was real. Problem is, even with today's technology, it would cost so much to do this that even a $100 bill it wouldn't pay for. So it's probably never going to take off. But what's interesting is this idea led to the foundation of quantum keys, as we'll get to. So to do something with this qubit state, we need to maintain coherence. Okay? We have to make sure that the universe isn't taking an observation. So once you've got a quantum computer with all your qubits running inside of it, if you were to literally open the lid and say, how's it going in there? Your computer just stopped working, basically. That's why quantum technology wouldn't be great for hard drives. You open it up and, oh, everything's gone. No backup to bring that back. It's going to exist in one of the other quantum universes we talked about. So to maintain this spooky state, you got to get some pretty extreme conditions. A lot of times temperature, it's got to be super cold. You have to have bizarre chemical mixtures isolating these things. We don't have time to go into everything, but these are some of the ones that are used. Nuclear magnetic resonance is interesting because when they tried to do factorization of a number, as we'll see, they ended up using that and accidentally discovering this one, discord. The idea that the difference between quantum particles and normal particles, the way they interact with each other, you get something called discord, and that can be used to compute, which is quite fascinating. It's almost like an accidental quantum state. Everyone's interested in how we can get this to work, because quantum computers won't work without this. So a whole lot of research is being done. The Nobel Prize in 2012 went to Serge Haroche and David Wineland. They both came up with ways to trap quantum particles so we can actually do something with them. Now, once you have these quantum particles, they're going to have to be applied to something that a normal computer is terrible at. Okay, so today, this morning, who was here for the keynote, you saw some of the weaknesses when you're local to a machine, let's say, and you want to crack something like this. You can have voltage modulations or what other side channel attacks you want in a processor. But when you don't have that kind of closeness to a machine and you just have a stream of data going, it's basically relying on the security of the math of two numbers. I mean, good luck finding the two factors of a 400-digit number. There are 10 to the 90 particles in the known universe. So you're looking for numbers orders of magnitude larger than that. That's why, in theory, this technology is secure when it comes to just guessing. So what can be done about this with a quantum computer? Well, Peter Shor in 1994, before there was anything approaching a workable quantum computer, just based on research at the time, he came up with an algorithm that proved on a blackboard, and was recently proved in a lab, that can find the factors of a number using a quantum computer. Now, how it works is incredibly complicated, but we can simplify it by saying this. It uses something called Fourier transformation, and that's used in other areas of science. It's used in astronomy. You can take wavelengths of light from one object that's entering, a telescope, let's say, and you can separate them and determine interesting things that are going on and what might be making it up. So we can also do that with the periodicity of prime numbers. So the quantum algorithm here will actually take every single possible pair of numbers that could make a big number and run this algorithm against them in a way that the waves either constructively or deconstructively interfere with each other. So what's fascinating about that is, in the end, you literally end up with only one pair of numbers spiking that could be the right answer. So if you have enough qubits in a machine, a quantum computer could slice through even the greatest PK in possibly milliseconds if it's humming along. And it might have to, because the first quantum computers might only run for a few milliseconds before we have to reset them. It's really hard to maintain coherence. Now, this was proven to work on a simple quantum computer with 4 photonic qubits. They were able to find the amazing result that 15 equals 3 times 5. We had no other way to do this. Well, we did, but even though it's not that impressive a number, it was done in a pure Shor algorithm way. It was also done with a thimbleful of this chemical that they found that the temperature wasn't cold enough to maintain superposition, and that led to the discovery of discord by mistake. So we know this works. Now, another quantum algorithm that's going to have a lot of implications for security is Grover's algorithm. Now, everyone knows a traditional database search takes n divided by 2 on average, right? If you have 100 entries, on average, it'll take you 50 tries to find the right one. Could take less, could take more. So Grover showed that using a quantum algorithm, and again with a wave interference pattern, we're going to end up doing it in the square root of n. And of course, when you ramp up into the millions and billions and trillions, square roots are much better numbers to deal with than half. So this could have a huge impact. DES, if we have the encrypted file and source available, we should be able to, in just 185 million searches, get the key, as opposed to 2 to 55. So that's huge. These are the only 2 so far that have fallen on blackboards and in lab experiments. And this was done in a lab experiment. Delft University nearby, UC Santa Barbara, teamed up. They built a simple quantum computer, the impurities in a chip. They were able to maintain superposition just long enough to do a run. So with the spin of a nitrogen atom and an electron, they were able to do 4 database entry search in one search consistently, showing that the algorithm is running, instead of what we were expecting to see, the classical 2. Now, this could have implications also in other areas of security. I think artificial intelligence, when applied to this, could have great impact on security scanners, for example. Right now, for example, if you're doing a web app scan, you're usually just running against a table of expected behaviors, very poor AI. It takes a long time, and you don't really get the greatest results. With something like this, it might be possible to access way more data, way more examples in a very small period of time. Just think back to Watson. If he could search through 500 gigabytes a second of data, imagine what a quantum computer will be able to do one day. So Google's obviously interested anytime you bring up the word search. So Google and NASA bought this D-Wave machine, and they put it in their lab. And I mean, they didn't publicly say it, but I'm thinking they found what most scientists found, that D-Wave doesn't really seem to have a working quantum computer. It has some kind of quantum-like behaviors, but it doesn't really seem to be one. The things they published that it can do as big press results, for example, finding the lowest folded protein, that could be done with a classical computer. It doesn't seem to be able to do anything that only a quantum computer can do. So Google mentions these other things they tried, like an efficient recognizer, polluted data handler, which will be useful to them. But it's obviously not a real quantum computer, because Google now announced that they're working with UC Santa Barbara to build, you guessed it, a true quantum computer. So obviously they found what everyone else has found. And it should be interesting. I mean, this will prevent the need for excessive indexing. You'll be able to do better fuzzy searching with a shorter period of time. So it would be pretty cool if we could apply Grover to the world. It's not just about cracking encryption. So no surprise, the NSA is interested. This really isn't all that controversial a slide, because I think everyone's interested. Everyone wants to be the first country or entity to have such a thing. But the Snowden documents revealed this roughly $80 million spend on something called penetrating hard targets. And that's definitely a quantum computer from what we could determine. What's interesting here is that Colossus is how all of this started, right? If you go back to 1943, Tommy Flowers at the General Post Office, he built the world's first supercomputer to do what? Crack encryption. And we're right back there again. It took a while, but we're right back to square one. Colossus wasn't pretty. It didn't fit in your house very easily. And it wasn't very commercial. But this is where we are. And interestingly enough, Tommy Flowers, the General Post Office was split off into British Telecommunications, which was privatized. So in a weird way, we work for the same company. So that's cool. All right, so once all this hits, we have to start looking to post-quantum encryption, right? There are technologies currently that haven't fallen yet. So as long as they haven't fallen yet, we don't have to worry about them in the near future. Now, I'm not saying they're perfect and there's going to be tons of flaws found with them in time, just like everything else. But these haven't fallen on a blackboard yet. So these might be worth looking at for the short term. One-time pad is very interesting because it's actually one of the first ones being used hand-in-hand with quantum encryption. But eventually, we're going to have to get to a point where the entire encryption process is done on a quantum computer. So it's going to be hand-to-hand combat in the supercomputer world. You know, it's like, you got a quantum computer? Cool, so do we. And then you're at the base level, like Fineman said, of working with the particles of reality. You can't go any lower than that. So now let's talk about quantum key distribution. So this is going to send quantum encoded keys via some medium, usually a fiber. When you send these keys, they have a beautiful quality of, if you take a look at them as an attacker somewhere down the wire, guess what happens? They become invalid, and we know this instantly. Okay? This is really eavesdropping proof if you do it correctly. Of course, you can implement anything poorly, even passwords with notepads next to a desk. But if it's implemented properly, in theory, anytime you take a look at a quantum key, it will destroy the key, and therefore we'll know that something's up. Now, this works today in combination with one-time pad and some other technologies. So BT partnered up with Toshiba, ADVA, and NPL, and Toshiba developed an ability to send quantum keys over the very same fiber that the protected data goes over. Now, before them, everyone was sending quantum keys through some dark channel that had to be built, and then other data elsewhere, and the two met. So we teamed up with them because they have the single path, and we were able to do it in the real world. So we sent it, as I'll show, over real live dirty fiber with phone calls and video and everything running, and we were able to decode the data on the other end. So to do this, they have to use some kind of protocol. So there's something called BB84. It's been around a long time. Toshiba modified it. I don't work for Toshiba, so I'm not given all the information. We're literally not allowed to open their boxes sitting in our lab. But they came up with something called T12, which is a modification of BB84, if you want to look into that. So we were able to take a real multiplexed path of 4 10G lines, and we were able to, in the middle of all that noise, inject quantum key data and send it over 26 kilometers of real wire from Industrial Park to Ipswich. So going over that fiber was everything. Like I said, phone calls, video, you name it. Now, using an ingenious timing method, we're able to detect when we should be expecting a photon with a quantum key and look for it and get it and decode it and so on and move on. Now, to achieve 10 gigabit speed, it's too hard to generate enough keys right now and send them. So you can use this in parallel with other things. So we used AES encounter mode. So basically, we injected the quantum key, sent it all bundled up, and then used the key at the other end, encounter mode, to take a look at what's going on. But you could just as easily do this any number of ways, which is the real beauty of quantum key distribution. You can use it just to generate random zeros and ones and create a one-time pad that is unbreakable, because it's really anybody's guess what it's going to be at any given moment. Or you can use it hand-in-hand with other technologies to just send a little bit. The speed we were able to send was 160 kilobit per second of key data, so that's why we had to kind of combine it. But I get the feeling that as this speed goes up, sometimes we've hit 300, a megabit per second, it might be possible to just send pure quantum keys and nothing else, which I think will be a worthwhile goal. And special thanks to Zoo and Lord, my colleagues at PT, for sharing the numbers. They typically don't like to. And with this, we're showing that when a quantum computer is built, it may be possible to be prepared from day one to protect really sensitive data. Now, keep in mind with this kind of setup, you're limited to distance. I think about 100 kilometers will be the max for a while. We're going to have lots of, like that EDFA, we're going to have lots of sort of boosters at the end. And we might have to have some kind of retransmission stations. But retransmission stations are tricky. They're not easy to set up. And one of the biggest things about quantum data is there's a principle known as the no cloning principle. So the number one attack people think might work against this, which they're wrong about, is that you can intercept a quantum key and then send a copy of it onto the person in hopes of fooling them. But it doesn't work. In the quantum world, if you take a look, you destroy it, and you can't clone data, thanks to the no cloning principle. So as a result, this will make a way for quantum computers to actually have a hard time cracking something going over the wire. Now, it's not quantum end-to-end, so obviously more work is needed in terms of having supercomputers at both ends that can make it purely quantum state. And with that, I think I actually ran over. So I guess maybe I could take a quick question unless they throw me off. And I'm here all week, literally. I know I blend into a crowd and everything, but if you guys spot me, I'll be the head floating above other heads. So any quick questions before they knock me off? Yeah.
Yeah, how about DLP? Is it still considered safe? Discrete logarithm.
I can't hear you, I'm sorry.
Is discrete logarithm still considered safe?
Yeah, for the time being.
That's wrong.
What?
Log is affected by short algorithms.
Yeah, I'm having a hard. Let's talk outside. I'm not gonna be able to hear you. Yeah. Okay. Thank you. So thanks everyone.